Hi, this is Lihui and here is the video for my interim report of the IE 413 semester project. My previous project is about the dimension, like a optimization of the vehicle's compartment. However, I tried the simulation tool and it just didn't work so well for me. So I decided to switch the topic, and my new topic is cross area optimization for 10 bus truss benchmark problem. And since it's a switch project, I'm a little bit lag behind regarding the schedule, so I need to work more to catch up with the schedule. Anyway, let's start with the problem. So the 10 bus truss problem is basically a benchmark problem, especially for different kind of like a algorithm test. It is first introduced by the Venkaya in his work Design of Optimum Structure in Computers and Structures in the 1971, and the problem is basically given a geometry of a structure which consists of 10 truss structures, and then two forces are applied to two of those nodes. You can see here they are node 4 and node 2, and it's very intuitively that if you are applying a force to a structure, the structure will deform. However, in the actual life, in our daily life, sometimes those structures, they need to stay stable, right? Otherwise, maybe it will crash or it will just it will hurt someone. In that case, several constraints are going to be applied to this structure to make sure this structure design is robust. So in that case, given the geometry, applying the constraint, one should be able to determine the cross area of each member in order to make sure this design is feasible in daily life. And that's why this problem is kind of like a benchmark problem, because starting in this kind of like a medium to small scale of problem, one can generalize those structural optimization problem. And yeah, this is a scheme of the problem, and you can see here there are 10 structures here and two forces being applied. So the problem statement is basically given the structure member's length, the Young's modulus regarding the characteristic of the member's material, and the length of each member. We are trying to optimize the cross-sectional area of each member. They are not going to be the same because the stress condition for each member in this structure, they will be different. And we want to keep this system robust so it won't fail. Here is the mathematical form of the problem, negative norm form, and basically we will minimize the f function, where the f function is just the cross area times the length of each member, because when we are building something, we try to basically fulfill the stress requirement, also maybe the displacement requirement. At the same time, we are using as least amount of material as possible because we want to save money, right? And we want to make sure the structure is robust, so no structure member is going to fail. In that case, the stress in each member should be less or equal than the less of the yielding stress. The amount of the yielding stress, and the displacement of each node should be less or equal than plus or minus 2 inches, because when you are building a structure, you want to make sure it's stable. It doesn't move so far, otherwise it's not feasible in daily life. And here are some design nomenclature and the material property. So f is just the objective function, a area, and the lambda, which is the specific weight of material, and a sigma is just the strength of member, blah blah blah. And then you can find it on my final report. I'm going to include it anyway, but Yeah, and these are some material characteristic because we are only optimizing the cross-sectional area, the Young's modulus and the specific way, and then also the length of the structure. I mean, the length of each member, they are fixed. Otherwise, there will be too many variables. However, if the algorithm is being like a derived, it is possible that the length of each member could become another design set of variable. In that case, there will be 20 variables instead. So I will see whether I'm able to add the length of the member as a design variable after my later discussion. So we have the constraint for the area. It should be greater or equal than 0.1 inches square, and then we have the length, getting the displacement limit and the input forces. In that case, a relationship between the stress and the cross-sectional area of each member must be built. Otherwise, no equations can be got in order to solve this problem. So in order to get those equations, generally we have force, we have displacement, and we want to solve for the unknown stress, right? So we can use the Hooke's law. And generally in the structural design, we are using a relationship called the structural stiffness metric, which can be derived using the Q equals KD relationship, where K is the stiffness matrix, D is the displacement, and Q is the global forces. So we treat the whole structure as a whole, and then we have the forces, we have the displacement, and we are able to figure out the K, where K is determined by the cross-sectional area of all those members. In that case, we can get a bunch of equations and we put it in the MATLAB to see whether we can solve it. In order to get the big Q matrix, one should always start with the small Q matrix, and then the K matrix. And then you can see here, if we are looking at one of the maybe a small member, we can determine the small K matrix, which is shown right here, and it is extracted from the structural analysis textbook. And the lambda, they are just the directional cosine of each nodes. In that case, we have the small k, and then you can see there's a E here and there's a A here. A is just the cross-sectional area of the member. In that case, the K is related to A. And if we combine those small coordinates of all those members together, we are able to get the big Q, the big K, and big D, and one should be able to partition the Q equals KD relationship, where the subscription U is representing the unknown and K is representing the known. You can see here, if we expand this metric relationship, there will be a bunch of equations. And we have the equation, we have the MATLAB, where we should be able to solve this problem. And this one is just a simple K matrix, which is extracted from the optimization in practice MATLAB is a textbook. So you can see here, in this case, the x1 and x2, they are just the cross-sectional area of the member. But I'm not going to use this metric anyway because the geometrical structure, they may be different for different structure. So here is the example, and then there will be another like D matrix, and we are giving Q. We multiply those out, we are able to get the relationship. Then we solve for it. So the scope of the project is to get a metric using the equations that I just covered, and they implement the MATLAB coding starting from the admin column we just used in the homework we are going to submit in today, and then I will use the ANSYS analysis to verify whether the structure is failing or whether the displacement is still in the range. So this one is just a simple ANSYS interface. We just put those structures in it and applying the force, applying the constraint, and one should be able to see how the displacement works and how the stress distribution works along the whole structure. And these are some reference for the project, and if you have any question, just let me know, any recommendation. And it's going to be a busy Thanksgiving break, and thanks for watching and have a great day.